let's talk kinematics. So, get my pen to write first. There we go. Okay, kinematics. Well, what is kinematics? It is the mathematical study of motion. All right. Okay, so the first thing we will mention here is the concept of a rate. Okay, so a rate. So what is a rate? This is essentially tracking change with time. So when objects are moving, their positions are changing relative to time. Okay, that's what we're talking about here. So we'll lay down a number line, and we'll just remind ourselves of some stuff that we maybe know from last year on this topic. Okay, so make ourselves a little number line here. And we'll imagine that this number line is, measuring something in real life. So you could think of it like a football field, say, or you could think of it like a track or whatever. And you could have your values measured out here in terms of meters. And we know going to the left on this type of a setup, it's going to be negative. Okay, so now what we can do is we can place an object, put some position on here, and we could say that this happens at time 1, okay, and we could call this position 1. We'll call this position 1, we'll call it D1 for position 1, okay? And then sometime later, we'll say this object has moved over to here. And we'll say that it's moved constantly, right? It hasn't accelerated, it's just moved, at regular intervals across this number line. Okay, so it's moved in that direction across the number line. We call this D2 and T2. You might also see this as DI, TI, TF, DF. So what that means is this is the initial time and the final time. This is the initial position and this is the final position. Okay, and we would say then that the difference between these two is delta D. So this is what you've how you've done this in the past. We're just going to change up our way of writing this a little bit. So this has a different way of being written in the IB kind of world. So if we're talking IB, displacement is actually going to be called S. Okay, so we're going to call this SI, SF. Don't ask me why it's S. It just is. And the change here, the displacement, right? How far out of place you are, is going to be called S, or you can also call it delta S. Okay, this is kind of like a calculus nomenclature. So later when you take calculus, you'll kind of see that a little bit more, or see it like this, as ds, rather than a delta symbol. So this symbol is from mathematics, or from the Greek alphabet, and it's delta. All right, so we would call delta S then displacement. And in this case, it's the same as distance. So this brings up the concept of vector values versus scalar values, which we've sort of talked about a little bit. But when we're talking displacement, okay, we attach a direction to this versus the scalar value, which is just d, or distance if you want. Okay, and to illustrate that, we could also say, okay, well, maybe an object starts here and moves to here. Okay, so in this case, delta S is actually going to be a negative value, right? Whereas the distance will still be positive, right? So distance is just 8, whereas if we're talking about displacement, then we have to say it's negative 8. So we are indicating the direction of travel when we're doing this, okay? So how does this relate to rates? Well, if we look at how displacement is changing every second, if you look, this object goes 2 meters every second. we would say then that its velocity is 2 meters per second, right? So its velocity is 2 meters per second. This has a velocity of, or roughly negative 2 meters per second. Okay, and that's just by looking and stating that this is, say, representing where the object is at 1 second intervals. All right, so when we're dealing with a rate of change in displacement, what we're talking about is velocity. I should say rate of change in position, actually. And this is a review. You know this from last year, okay? The formula for that is just V is equal to delta S, okay? So displacement over time. And if we expand that, what we mean is final position minus initial position for final time minus initial time. So if we were to look at this motion on a graph that relates position to time, it's a little longer. Okay, we have essentially two motions. So we'll look at the yellow motion first. Starts at a value of -6 in position, goes up to a value of 7. So it starts down here at -6. Ends at +7. Okay, and how much time did we say that happened over? So 7 seconds roughly. So we should probably just keep it even. Let's start it. Let's just move it over here so that my numbers are actually correct. There, we'll do that. Uh-oh. Okay, that's better. All right, so we'll start it down here at -7. Go for 7 seconds. So we go 14 meters in 7 seconds. You're going to get just a graph that looks like this. So what are we saying here? Well, basically we're saying every 1 second this object moves 2 meters to the right, okay, in the positive direction. So what would we call this graph? We'd probably call this position versus time. Okay, position versus time. Here's time in seconds, and here's position in meters. All right. You notice we just have a straight line here. Okay. So I want to remind you that if we're looking at a line like this, okay, you realize that if I'm talking about delta S versus delta T, okay, let's see what I'm really talking about here. So if I look, delta S is represented by this, right? Final minus initial. Or in this case, 7 minus -7, which is equal to +14 meters. Okay? And then time here, delta T, is equal to final time minus initial time. In this case, it's 7 seconds minus 0 seconds equals 7 seconds. And we said then that velocity was equal to delta S over delta T, which is 14 meters, 7 seconds, which is the 2 meters per second that we saw up there. Okay. What I also want to emphasize here is that this is also called the rise, right? Or in math class, you might call this delta Y. And this you might call the run, which is delta X. So what we're saying here then is that velocity is the slope of a position time graph, right? Velocity is the slope of a position time graph. Okay, that's important, and we're going to need to use that information a little bit later. All right, so now I want to take the position time graph for this motion, and I want to graph it out as a velocity time graph. Let's see what that's going to look like. So it's actually going to be sort of a boring graph. Now we're still talking about the yellow, right? We could, if we wanted, I'm not going to go through all of this trouble, but just before we move on, we could look at this as well. So this starts at 5 and moves to -3 over 5 seconds. It starts there, moves down to here, 1, 2, 3, 4, 5, and -3, something like that. Okay, so that moves in the negative direction. All right, so you have a negative slope, so you have a negative velocity. Right, makes sense. You're moving to the left as time goes by. Okay, so let's go back to the green guy there, and we said that that's 0 meters per second. Let's just fill out our graph here. This is velocity measured in meters per second, right? What we're doing here is we're taking the slope of this graph, we're graphing it out on this line here. Okay, so we have time in seconds here. And we notice that for this motion, the velocity is always the same, right? It never changes, and it's always at 2 meters per second. Make sense? Now, let's get our formula here, okay? So we could rearrange this, right? We could say, well, why don't we write it like this? Our change in displacement should be equal to whatever velocity we have times the time that that velocity happens for. So what we're saying here is something like, let's say you traveled at 100 kilometers per hour for 3 hours. Well, you've gone 300 kilometers, right? So we're going to say, all right, 2 meters per second for 7 seconds. How far did we go? We went 2 meters per second. There's our velocity times 7 seconds equals 14 meters. So on this graph, what we're representing by that is actually the area under this graph, right? The area under this graph is shown to us by this formula. It's velocity times time, and that gives us this area, this rectangular region here. Okay, so that's important. So we said velocity is equal to the slope of a position time graph. Okay, and then we're going to say that displacement, I don't like that. Displacement, it's actually, yeah, it's displacement equals area under a VT graph. Okay, so that's review. Now let's talk about accelerated motion. This is a little bit more interesting. So we're going to make a new graph and a new scenario. And we're going to imagine now that something is speeding up. Okay, so let's talk about accelerated motion. So we did a little experiment here off camera where essentially we took a ramp. All right, took a ramp at some slope, put a little motion detector on the ramp. So like a magic eye, essentially, that is able to look at the object as it rolled. Oh man, that's nasty looking. As it rolled down the slope. Okay. All right. So what does this thing see? Well, this thing sees how far away the object is. You know, it's in 10 centimeter increments. And what it does, right, is it plots out what this looks like as it speeds up down the slope. So if we were to take pictures, at like every, say, tenth of a second or some fraction of a second, right at the beginning, you would see data points that are close together. And as time goes by, right, as this object speeds up, the amount of distance it's covering in every second, or the increase, if you want, in displacement versus time, looks like this. So what we're talking about now is we're talking about an increase in velocity, right? These are equal time periods. You can see you're covering more distance as time goes by. That makes sense. If you graph out that information, you get a nice curve. Okay, you get a curve on the graph. Why is that? Well, if you look at 1 second intervals, you can see that the amount of distance covered, from 2 to 3, which is represented by this value right here, okay, is smaller than the distance covered between 3 and 4, which is represented by this value, okay? And from, we can't quite get back to 1, but the first one is smaller. So here's the distances that is covered in each of these 1 second time intervals. And you can see that that's growing, right? So what we're talking about here, right? We're talking about basically the average slope, if you want, for each of these time periods. And you can see that it's getting larger, all right? Now, is that what this is showing? Sort of, but not really, okay? What this is actually showing is it's showing the instantaneous velocities, okay, as time goes by. So to get an instantaneous velocity, what you do is you grab a line and you make that line tangent to your graph at a whole bunch of different points, right? So let me just move these into place here, and we'll say that what the tangent line, that's probably a good tangent there, that's probably tangent there, I would say, and this might be tangent here. I don't actually think it ever gets quite to that height. These tangent lines are graphing for you. If you find the slope of the tangent lines, they're graphing for you the instantaneous velocity at that point in time. All right, so if I go and I find the slope for, an infinite number, if you want even, of tangent lines all the way along this slope, and I graph it out, what I'll get is something that looks like this, okay? Now, we're not really interested in this part, okay? This is where it came to a stop, but we're interested in this nice smooth slope here. So what this is showing is a gradual increase in time, or a gradual increase in velocity as time goes by. Okay, so this is showing you an acceleration, right? So we generate this graph by finding slopes from this graph. Okay, so we're being a little more sophisticated than we were before. Before, we had something with a constant velocity. There was no curve in this graph. It just, its position changed equally at all times. Now we have a position that is increasing, a velocity that is increasing, so we have a curve on this line. So just to reiterate, right, the same is true that the slope of a dt graph, but now the slope's always changing, gives us this. So what must also be true then is that the area under that graph gives us what? What does the area under a velocity time graph tell you from before, from earlier in this very same lecture? What do we say it gives you? The area under a velocity time graph gives you, good. But now look, we're finding an area that is no longer a rectangle, okay? So let's work with this. So we're going to generate a new formula. And actually, start with a little problem. So a vehicle accelerates from 0 meters per second to 10 meters per second in 5 seconds. Okay, so I mean, we're looking at this as an example. If we were to graph out what we're talking about here, though, we would see something like this. Okay, so this is your position, this is your time. The car is speeding up. You get this kind of curve. If we look at the velocity time graph of the same motion, this is where we actually have information. It goes from 0 to 10 in 5 seconds. 2, 3, 4, 5 seconds, 0, 10 meters per second. Okay, so we'll graph this in, and there it is. There's a graph of that motion as well. Okay, Now the question might say, how far did it go while accelerating? Okay. So if we look here, all right, we remind ourselves that this PT graph, right, is found, or so the velocity time graph is found as the slope of the PD graph. That's looking at all those tangents as we go and then graphing them on this. And that area finds this. So the question is, how do we find the area under a graph when we have acceleration, right? If we have a constant acceleration, that's easy, right? It's just v times t. But here we have a changing velocity. So how do we deal with that? So here's the answer. So the first thing is, let's look at this area. Let's look at this area. All right, so there's the bag of it, and I'm just going to do this. Okay, and we're going to say the area, right, is half of this square, isn't it? It's half the size of this square. So we're finding like the area of a triangle essentially, right? So base times height divided by 2, and we're finding the area under here. We're going to do a slightly different method. We're going to do that method after, but we're going to do a different method first, okay? We're going to say, well, we can also find half of that rectangle by doing this. Cut it here, and we can find the area under here, right? So half of this space, this triangle, this area under this graph, is here with the blue dots, or it's equally valid to say that that area is equal to this spot, this stuff right under here, this rectangle under here, okay? So what are we doing here? Well, here's your final velocity. In this case, it's 10 meters per second. Here's your initial velocity, 0 meters per second. It doesn't have to be, but in this case, it's 0 meters per second. And here's your time, 5 seconds. So we want to find this rectangle. What we would do is we would just get the average of these two values. So VF plus VI over 2, right? That would give us this. So in this case, it's 10 plus 0, 5, right? So what we're saying is the area under this triangle is equal to the area of this rectangle, and the value that you'd get for that is 25, right? So this is what we're essentially saying. For an accelerating object, the distance that it covers, we're going to write some new nomenclature, is u plus v over 2 times the time that it took. So what's u? Well, u is just a new way of writing initial velocity, okay? So in our world, we're just going to change vi to be called u, okay? And then that leaves this to just be v, okay? This is the way that this is written now. And in this case, u is 0 plus 10 divided by 2 times time, and you get 25 meters. So a car accelerating from 0 to 10 meters per second over a time period of 5 seconds will cover 25 meters during the acceleration. That's new, okay? Just to clarify here, because I might not have been clear, u is the initial velocity. V is final velocity, and S is change in displacement, or sorry, is displacement. Not change in displacement, change in position. It's displacement. Okay, so just going back here, if we now take the slope of this, right? So here we're talking about change in velocity, and this is change in time. what we can generate, right, if we look at the slope of a velocity time graph, so skipping over this problem now to finish up with acceleration, we can define acceleration as equal to the change in velocity divided by the change in time. So now we can generate a new graph, which is an acceleration time graph. So if this is velocity and this is time, okay, and we see that our velocity is increasing as time goes by, okay, and then we take that graph and we do a rise over a run, right? The change, the rate of change in velocity is called acceleration, okay? So if you look, essentially we get this kind of an order going on here. You know what, I'm gonna just draw that now. There's acceleration, there's time. Okay, you would expect that this graph then has a constant acceleration, just like that. Okay. So one more thing we can write is that the slope of the velocity time graph generates the acceleration time graph. So that's this here, put it over there. That's the slope. And then what do you think happens if we go the other way? What do you think the area under this graph is going to generate for us? Well, we're going to take this formula. We're going to say then that delta V should be A, acceleration, times time. So the change in velocity, how much this velocity changes, is going to be the area under that graph. Okay? So now we have a relationship here, and if I grab this stuff and just move it down, see if we can tie it all together into one big scene here. Pull this down a bit. And up above here, I put the corresponding displacement time graph that generated all of this data originally. What we should be able to see is the whole picture. And I'm using improper nomenclature here. It should be S. Okay, so slope goes there, and area goes there. So this is how these are all related.